Thank you, and hello everyone in California. Greetings from Colombia. This talk is a redo of work that has been done for over a decade now, and it's not just my work; it's mainly work that was done based on efforts from the Southern California Earthquake Center. So what I'm going to share with you is an experience of a larger group, but mostly based on what I can speak for myself. And it's always good to mention that this has been going on for quite a good number of years. Okay, so I started working on this in 2005 or so, and all sorts of different efforts have been done over the years in some different event scenarios, and then different efforts in terms of either verification or validations have been done. And then the factors, as Martin and others were mentioning before in the case of the source, then here in the ground motion level are many as well. And some of them relate to the physics, some of them relate to the computational efforts, some of them relate to uncertainty, numerical accuracy, and all sorts of different factors. Just a reminder that I'm going to focus mostly on validation, but then it is always good to mention that before validation, one needs to do verification. And then what I mean by verification is to make sure that the models and the implementations that you're using are correct to a certain extent, so that you can go on with comparing with the observations or other data that can actually validate your results. And over the years, we did that for different earthquake simulators, different ground motion simulators, different velocity models. And this started as an effort of different people, different groups, and so on, with the shakeout scenario. And here are some old results from 2010. And what was done here was mostly to make sure that different people with different conditions can agree on a common ground in terms of inputs and results. And these efforts were obviously positive, and then over the years that allowed us to move on to the validation stage. And for that, we use different goodness of fit metrics. There are, as in any other market, there are different products you can buy for this in terms of the tools that you can use to decide what are the levels to which you define something as excellent, good, fair, or poor. And there are some of these that are more quantitative, and there are some of these that are more qualitative. And then the reason I bring this up is because thinking of the questions at the end of the panel before, one needs to consider that the results depends ultimately on who needs it and who does it. Because you can basically find everything for everyone. And then you need to make sure that you understand what is it that you need and how you can compare it to what you need it for, okay? So here are some results from validations done for moderate magnitude earthquake, Chino Hills in the LA area. And then for this, we had back then over 300 observation points. We did obviously comparisons one-to-one, and you can find fair, poor, good, and excellent fits for this. Also, depending on how you see it, if you see it based on energy, based on response spectra, Fourier spectra, the time series, and in any one of these different perspectives, you will find things that are good and things that are not good. And here are some examples for Fourier spectra. And here are some goodness of fit maps that show you over the whole area of simulation how good you can do compared to the data. And again, many variables, so you can do this in different directions, components, and so on. You can also do it in frequency bands, and then depending on the frequency bands, you will do better or worse because you have more accuracy in terms of resolution or in terms of the models that you're using for that. Typically, the higher frequency, the higher you go in frequency, the poorer you go in the fit, because of the resolutions of the underlying models for your simulations. The velocity models happen to be one of those several factors, perhaps, in my opinion, the one that matters the most. And then we did this for different velocity models as well. And then we detected problems in the velocity models that others devoted efforts to improve over time. And then based on that, you get different results in terms of the time series again. And then again, you can repeat this once again and again and again for all different combinations. So here are results of summary results for 4 different velocity models for the same event. And then now when you have one event, and I resort to what Martin was mentioning before when he said, well, what is a realization in what we are talking about? So here are 4 different realizations based only on changing the velocity model. And then also you can also compare this, how these velocity models do better or worse if you keep everything else the same, and then you use as a parameter for comparisons how the goodness of fit deteriorates or improves with distance, for instance. And that gives you a measure of an indirect measure of how good is your attenuation model within the whole simulation. And then since you can do this also for different velocity models, you can also compare how they do for different frequency bands using different velocity models for the same supposedly realization. And then you can also start varying other things like the maximum frequency, for instance. So here are comparisons for different velocity models with different maximum frequencies in the simulations. You can also detect through this how good is your source. For these results so far, for this moderate earthquake of Chino Hills, were done for a point source. So we are far from the world that were described before in terms of dynamic rupture simulators, and we were using just one point. And we moved on to doing kinematic sources, so we extended the area of rupture and we give additional details to the area of rupture. And you can also, based on the data, come back to that and gain a sense of how complex or not is your source model as well, compared based on what you infer from the data. So here the red dotted line is that very moderately simple kinematic rupture, and then the blue continuous line gives you an idea in terms of frequency of how much more complexity the data is telling you about the true source, which you obviously don't know for sure. So moving on, you can also then do this for multiple velocity models, for multiple events. So we did this for a large set of events, all in the greater Los Angeles area. And then we repeated the same thing for all these many events, okay? And then we did the same thing for all the combinations of the velocity models. And so that gives you an idea of how much your goodness of fits on a regional scale will vary based on different velocity models and different epicentral locations. But very simple source models. All these were point sources. And then you can use that as an indirect measure of identifying, depending on the location of the earthquake for a given region and a given set of velocity models, what are the conditions that are most favorable to obtain good validation results of synthetics compared to data. And then so what you see here is 2 different events, 4 different velocity models, similar location, and then you can also look this through the lenses of different frequency bands. And if you do this in all sorts of different combinations, you can also have an idea of, okay, out of the sample of velocity models or source models that you have, which works best for on a regional level for multiple events. And what this allowed us to do back then for Southern California Earthquake Center was to have a much clearer sense of what version of the velocity models was the one that most consistently performed well. And I say well and not outstanding because it also depends on all the other factors. Now, then we went back to see if our verification and our validation efforts over the years could sustain as we gain computational power and pushed the efforts to higher frequencies. So we went back and repeat a small moderate earthquake for different codes, okay? And when I say different codes, I also have to mention different numerical approaches, okay? So we have finite difference on one hand, and then we have finite elements on the other hand. And for this, we did, again, a robust combination of different factors, different velocity models, different attenuation models, different source models, and different domain sizes in terms, so that we could compare what was going on with the results. And then point source, and then a simple kinematic source and a more complex kinematic source, okay? And once again, you throw all this into the mix, and then it gives you an idea of all these different factors using different codes, using different models, how much variable are your results in terms of validating with data. Now, key point here is that so far we used back then moderate earthquakes in order to avoid questions about plasticity, nonlinearity, frequency variable attenuation, and things that that the physics have, but that you cannot fully embrace all of them at once. Again, different frequency bands, different performances. You could sense again a sense of how good are your models and how variable are the results. More examples of the same now for different for different source models. And then later in 2017, we published in the World Conference a small paper that was an attempt to combine all these different factors in a single for a single set of events, and see which of these factors was more predominant over the others, or was more influential. So again, different velocity models, different minimum velocity for the numerical models, different numerical accuracy in terms of how many points per wavelength we could use for the meshes and so on. Different attenuation, different Q models, source, and also varying magnitudes, because for these point sources we realized that the magnitude that we typically get from the source inversion could have certain level of uncertainty. And then the figures in the next couple of slides, I'm not going to get into detail for each one of them, but it's just to mention that you have plus plus or minus a number in terms of the goodness of fit. And if you were moving in a scale that 0 is a very bad fit and 10 is an excellent fit, then you have here plus minus on the range of 3 to 4, even in the extremes, okay? But mostly it stays in the range of plus minus 1 or 2, okay? So here is, for instance, comparisons between how much influential is one velocity model compared to the other one for a point source on the left and for an extended source on the right. Here is the same thing, but comparing attenuation models on the right, and then factors of comparison, factors of that determine the Q for the velocity models. So different attenuation models in terms of the mathematical approach and in terms of the physical representation. That's what I meant to say. And then you continue doing this, and then you get this sense of which of these factors are more relevant and how much they move the needle. For instance, here, the minimum velocity 200 versus 500 is irrelevant, but this is irrelevant because these simulations were up to 1 Hertz. If you push that to 5 Hertz, then the 200 meters per second might be a much more relevant factor. Accuracy, numerical accuracy on the right, number of points per wavelength. Now, all these two also come here to other considerations that I'm not going to get into detail into this, but for instance, what is the purpose? What are these simulations going to be used for? Okay, can you do hybrid approaches? Different metrics to measure will give you different sense of validation. Whether if you include topography or not, Roberto mentioned something about topography earlier. If you include plasticity or nonlinearity or other measures of energy losses in your simulation. And then at last, if you include the built environment, connecting to what Dave was mentioning at the opening of the workshop, thinking of tomorrow and the future. So here, for instance, is a setup that we did a couple of years ago in terms of comparing different models in terms of the velocity model, the structural model of the simulation, and how much it is influenced by the fact of combining the deterministic models with the probabilistic models, and how much they affected the validation on the range of the longer periods, low frequency, when you include the 3D models compared to the 1D models. When I said that if you use different metrics, obviously you will get different results. Here was an attempt by Kosnevich and myself in terms of reducing the number of factors that we use and try to identify which were the factors that matter the most for validation purposes. So we found that response spectra and energy are two measures that are good proxies to understand how all the other metrics perform when you do validation. And then here is an interesting attempt of understanding how much variability you will see on the ground motion if you include soil structure interaction, if you include the structural models, even if simplified, into your ground motion models. And then if you include multiple buildings, how much variability that will introduce into your sense of observing, if we can truly observe the ground motion, given the areas we lived in and where the instruments are located. So in closing, what I'm going to say is that this is an old slide, but I brought it back because the velocity model matters a lot. The minimum velocity in the model matters depending on what is your computational capacity. The numerical resolution matters a lot for verification, but it may not matter that much for validation because it is much more difficult to compare with data. Attenuation models matter significantly, especially if you're interested in the far field, but if you're interested in the near field, maybe not that much. Source models and source uncertainty, nonlinear soil, topography, and then, as I mentioned at the end, size-city interaction. And then aspects in which I think we continuously have to redouble efforts. Inversions, especially for velocity models, is my take, but I'm quite sure that others will say for the source. Focus on energy losses in terms of anelasticity and nonlinearity. Understanding the variability, and I think the question that Brad Agar posed earlier in the chat was in that sense, variability and uncertainty. What is it that we really don't know, and what can we control? And then the importance, and I think we'll see more from Dave tomorrow in terms of what the center is trying to do and what you guys are trying to do at Berkeley, is to use workloads that can accelerate and allow us to do many more simulations to understand how all these factors influence the results. And now you notice that in the last two slides, I put that little elephant there. And I put it there because nowadays, in the last 2 years, especially 2-3 years, I wonder how much we can continue to devote efforts in terms of computational effort at the larger scale compared to the up-and-coming competitor of artificial intelligence, and how much we can truly understand the physics if with certain level of physics in the AI technology, much faster, the alternatives are much faster into reaching to something that is reasonable. And then I think that's the key question for all these years that I worked on this with SCEC in conversations with engineers. What the key question was, is it comparable to what we use in the practice? And then we can have very interesting questions about the physics, but if there is a faster alternative that is acceptable to a certain level to the need of the client, and the client meaning an engineer, not necessarily in terms of in commercial terms, then that is something that we need to consider in terms of independently of how much interested we are in about the physics. And with that, I will close.